welcome everyone. I know we have the after lunch slot to do quantum mechanics, crypto mathematics, and how that intersects with cybersecurity, so should be a good day. I've had a lot of conversations with folks in the room, so I'd love to hear more about what you're most interested about this space. Give you a quick background on where we stand with three parts of this ecosystem, the quantum ecosystem, which today is probably where AI was 5 years ago. So there's three pillars to it. It's quantum sensing, quantum communications, and quantum computing. Quantum computing gets the most headlines because it promises to break all of our modern encryption systems today. It also promises to transform huge industries, the pharmaceutical industry, material science, battery technology, financial networks, and so on. It's really a critical space that a lot of people don't understand how big this is. The difference between a quantum computer, a very modest-sized quantum computer, these are coming in the next few years, compared to all the possible classical computers that we could ever build with all the atoms in the universe, is vast. So just to give you a sense of perspective on why this is so critical going forward and why so much money is going into this space, a quantum computer operates on qubits. A classical computer operates on bits. With billions and billions of bits, with thousands of supercomputers around the world, you could never compete with a very small quantum computer with just a couple of hundred bits. In fact, with just 300 logical qubits, you have more computing power than all the supercomputers that could ever be built with all the atoms in every galaxy in the universe. That's an extraordinary amount of power, and it's the growth in each additional qubit to the power of the computer grows by 2 to the power of n. So every qubit is an exponential growth in the power of that system, unlike regular computers with just adding a few more bits doesn't really matter. You'd have to add a lot more bits. So that's why big governments, especially China, has really outspent everybody else in the space and made it part of their future roadmap, how to dominate for the next 100 years. It's one of the three pillars in their community, in their industry, where they know the difference between the haves and the have-nots in the future is having access to quantum computers. The advantage in many cases is insurmountable. And in today's talk, we'll just talk about the communications and cybersecurity piece, which has huge economic impact for the United States. The three pillars in China are AI, energy, and quantum, all things quantum, computing, quantum sensing, and communications. But today, we're only going to focus on how that breaks cybersecurity and what you can do about it. What are the practical steps that you can take today to do something? My name is Denis Mandich. I'm the CTO and co-founder of Decrypt. We're a post-quantum systems and cybersecurity company. We build systems that are both quantum safe and quantum secure. I'm also a co-founding member of the National Quantum Economic Development Consortium, which is funded by the federal government to be able to compete with other big industries around the world, including the consortiums in Europe and China and elsewhere. The Industry Advisory Board for the Center of Quantum Technology was founded by the National Science Foundation. Some of you participate in some of these grants already. This is critically important to include every sector in the US on this problem. We just don't have enough physicists and crypto mathematicians to be able to beat China, who are graduating about 20,000 of these people every year by the year 2026. Founding member of the Regional Mid-Atlantic Quantum Alliance, which is all the universities and big vendors in this area to try to get them to that quantum safe state. Also, I'm on the standards bodies. I've been asked by some of the financial industry folks here about that. So the standards bodies are really pushing this for the financial industry, which is what Dillinger said, that's where the money is. We have to fix that problem or we're going to see banks being emptied of funds and going out of business very quickly. We recently published a paper on how to assess your quantum risk and what to do about it. What are qubits, all the things that you really need to know about this space before you get involved. I'm on the ITUT, I'm on the Forbes Technology Council, I'm a 20-year veteran of the intelligence community, so I saw a lot of this from the dark side, what China was really doing to this country. I'm also a physicist by background. I think 10 years ago, General Alexander, the head of the NSA at the time, said it best, this is the single largest transfer of wealth from one country to another in the form of IP theft. That IP theft really means something for all of our industries because it's overtaking our economy and it's unsustainable. That was 10 years ago. I'm sure everyone here isn't a cryptographer or a physicist by background, so we'll just cover some of the basics. Cryptography is really just how to get information secretly from one place to another when you know there are adversaries involved. So there are two major requirements that we have to have. One is the secrecy of the information that we're transmitting in that encrypted state, the algorithms that we're using to do that. And the other is authenticity. That's absolutely critical because, as we always talk about in cryptography, Alice and Bob need to communicate and be sure that I'm actually communicating with the person I intend to, that Alice knows that it's Bob that she's sending that encrypted message to. If Eve is in the middle, then you may be sending perfectly encrypted information to Eve, who then decrypts it and modifies it and re-encrypts it to Bob. So authenticity is absolute. We have to have that to have any level of security. So all of the security proofs for all of the algorithms that we're using today, and we're going to talk about the NIST competition and several other pieces here, require a first step in this process. That's the ability to just generate a true random number. A random number is the secret keys that we use to encipher all of the plain text and turn it into crypto text. That key may actually be shorter or longer than the messaging or the data that you want to encrypt. And that's critical because it's very hard for computers to use noise and other thermal processes inside of a device to generate a random number. People may not realize this, but most of those systems are chaotic. Chaotic systems are governed by very simple mathematical equations. They may be hard to predict. They may be difficult even, but it's not impossible. So really one of the things we need going forward is that ability to just do that step one in all of cryptography, which is just generate a random number. We only know of one truly provable random process in the universe, and that's quantum measurement. We perform a quantum process, we do a measurement on it, we can get an absolutely certain 0 or 1 that provably could not have been known beforehand. So real quick short history of cryptography. It's been going on for thousands of years. You all had a Captain Crunch recorder ring at one time. The Caesar cipher I saw was in another talk earlier today. There's a little jargon that we have to get through. There's two types of algorithms that we use today. Symmetric is when we have the same key that encrypts data as decrypts the data. That's symmetric key cryptography. AES is the most well-known system in that space. And then asymmetric, which is our public key infrastructure. That's when we have a public and a private key pair. Those are typically only used to encrypt the symmetric keys and exchange those between users so they can actually encrypt the data. The reason for that is that those algorithms are computationally intensive. They require a lot of compute resources, meaning battery power on mobile devices and so on. And many small devices like IoT, sensor systems can't support that. They fall into two other major categories. One is information theoretic security. These are the algorithms that we can use, discovered and proven in the 1940s by Claude Shannon, the father of information theory. There can be no advancements in physics, mathematics, or computer science that can break these algorithms. So we can freely encrypt with these algorithms and transmit everything in the clear, let everyone in the world capture, and it won't make any difference. The other type is computationally theoretic secure. These are algorithms where we believe they're secure against the computers that we have today, even the quantum computers that are coming down, but we don't know for sure because there's no absolute mathematical proof that they are safe, and we're going to talk a lot about that today. So the difference between those two categories is very easy to remember. The first is quantum secure. We know absolutely that quantum computers cannot break them. The second is quantum safe. We believe or hope, it's a little bit of fairy dust here, that they are in fact secure. So in the US government, I met some other government folks here. There's two suites of tools that are known. The secret ones that are only used within the government for really sensitive, high-value data, diplomatic traffic, intelligence communications, and so on. And then the other suite, which is everything large enterprise uses, RSA, elliptical curves, AES, and so on. The difference here is that all those publicly available cryptographic algorithms are open to scrutiny by researchers from anywhere in the world, whether it's China, Russia, North Korea, Iran. The private ones are only available to scrutiny by crypto mathematicians at DISA and the NSA. And we believe that's very strong because they have more of those people than any university or any combined group of universities in the entire world. So they know what they're doing. They got it right internally. It's open to scrutiny inside the government, but not outside the government. And that goes back to a fundamental principle in this space is no security through obscurity. You can't say that you have a proprietary encryption algorithm because everyone should believe that that's snake oil and they should question everything you've ever done. So this is the public key space that you're all familiar with. PKI infrastructure, invented in the 1970s. The basic architecture is Alice and Bob each have a public and a private key pair. They use those to exchange and deliver secret symmetric keys between them, and those symmetric keys use that same channel to encrypt data and send it over the wire. And we also assume at all times that that wire is controlled by the adversary, but we still have some level of security assurances by using this mechanism. Now, the issue here is a little bit fundamental because this was invented in the 1970s at a time when a single copper wire and a handful of switches connected to users around the world. We don't live in that world today. It does not leverage the cloud. It does not leverage virtualization, containerization, and all the modern network infrastructure that we use today. It's highly redundant and decentralized, and that's what we should expect from systems going forward. So public key infrastructure and end-to-end encryption are at the heart of most of the secure systems that everyone probably uses today for messaging and other applications. The problem with the background and the architecture of this system, it was designed when the internet was just coming alive. It was the 1990s, the early 2000s. The first generation of these cryptographic standards was just coming online. And the internet evolved for data mining. It did not evolve for security. It evolved for data mining with the purpose of selling ads and personalizing information that you receive over the internet. That's a big problem today because we have to go undo a lot of those systems to actually get into a state that is absolutely end-to-end encrypted. This becomes an even bigger problem when all the software and hardware is developed in places outside of the US, which might have different standards, which might have cut corners on some of these systems, and that's resulted in some of the biggest security holes that we've seen today. And again, I've shown a couple of these that have come up just during COVID. This is companies that are effectively, in some sense, getting victimized by foreign vendors. Are these supply chain attacks? Are these just mistakes that weren't caught in manufacturing and so on? So one of them is the security tokens that we used in the US government. These are FIPS certified devices that were manufactured in China. They theoretically have very strong encryption, but there was a flaw found in them that reduced that secure space, that key generation mechanism by 80 bits. When you reduce that key space to something that everyone in the world can figure out or knows, you've reduced the overall security of your entire network infrastructure. We have terms in crypto mathematics like end-to-end encryption. It means something very specific. But in industry, these terms have been modified to mean whatever people want them to mean. In this case, the developers in the Zoom background protocol said end-to-end encryption really means end-to-end to Zoom and the endpoint, and then that endpoint to the other person. Well, when those keys are all generated in China and those video calls are done on servers inside China, you don't have any level of security. You have no assurances. They were fined $100 million for that. Probably not, they probably didn't know. They probably did not realize what some of the developers there were doing or why they were doing it. This goes back to the fundamental issue with step one in all cryptography, generating that random number. NIST has already come out and multiple times told us that there's no mathematical test for that. You can't run statistical analysis on a bunch of numbers that output from a black box and say that they're random at all. All the digits of pi are deterministic. We know what they are. There's no randomness in there at all. They passed none of these harder tests, which is where did the random number come from? What is the physics behind that device that produced that number? We're going to talk a lot about that at the end of this talk. So where is encryption used? It's used in places that it was never meant to be used. It was never meant to be securing things like cryptocurrency and crypto wallets. And so now we've seen the first generation of attacks on these systems and Bitcoin solutions that we're seeing coming out of the banks, where if I can calculate with a quantum computer or find a flaw in the mechanism that made that private key and that asymmetric key exchange, it doesn't matter if you're using a secure algorithm to transmit your keys to the blockchain, to transmit your data and transactions. If I can get your private key, and this has happened many times already, I can pretend that I am you, and I can force an immutable transaction on the blockchain that transfers all of your Bitcoin, Ethereum, or whatever you want to myself, and there's no one that can say that that's not true. This transcends cryptocurrency, goes into digital information, digital signatures. If I have your private key for a digital signature, I can forge a document that goes to any bank that's legal tender that says, I own this bank account now. I am the legal inheritor of everything you left behind for your children. Those things are already happening today, and they're coming. I like to always give one really interesting case. It's called the Ethereum bandit. He went out and said, all these crypto wallets that people are making homegrown applications on, what if their randomness generation for making that private key is so bad that it's not a 256-bit number, it's the number 1, it's the number 2. It doesn't cost me anything to go out and try that transaction on the blockchain, and he did that. And before people realized that he had taken 25 million in Ethereum, just by guessing the numbers 1 to 7,000 or something like that before they shut down the network. This has happened many times with other networks where they're not making it public. So if you see these older Bitcoin wallets and other cryptocurrencies suddenly come to life after a decade or more, when we think that the original owners have died, you can bet it's someone just guessing keys, because that's the easier way to get that money rather than trying to break the crypto behind it. So the greatest threats are across the financial networks, our critical infrastructure, and the data that we hold most dear, our private information that we don't want to share with anyone else, which is why we use these communications mechanisms. These vulnerabilities, even before quantum, persist almost forever. If they're in firmware, embedded hardware systems, they're in software packages that we all use. Many of you have lived through some of these at the bottom of the page and recognize them. Many will find SHA-1, a deprecated hash function, in live systems today. They're very hard to remove. They're very expensive to re-architect some of these systems. Deploying patches is unrealistic in many hardware deployments. Intel SGX, this is, if some of you are hardware folks here, that's the holy of the holies inside their CPU. These have now been compromised. That's in your CPU, in your laptops, in your desktops. You can't just rip out the CPU. Patching these systems and fixing these problems degrades their performance over time, and then they just have to be replaced. The top one, we'll spend a little bit more time on that later. Cyc is one of the last 2 finalists in the Post-Quantum Cryptography competition held by NIST, which will be our next generation of standards coming as early as 6 months from now in 2024. We all have to transition to these new standards for PKI. Cyc was broken by a regular laptop. I said in the beginning, all these algorithms do not have any mathematical proof of hardness. We don't know for sure that they can't be broken. And in this case, one of the strongest algorithms with one of the strongest security parameters behind it was broken by a 10-year-old laptop. If that had been deployed and installed on a huge user base, TLS, what have you, all those systems immediately become transparent to our adversaries. You can't just swap these algorithms out very easily. The future requires us to be crypto agile, meaning be ready to replace these algorithms, hot swap them out on a moment's notice. That's not an easy thing to do. Most of these systems are very complicated. It's not a light switch. There's an old saying in the intelligence community that complex systems break in complex ways that are almost invisible to everyone and take years to find out. I don't have to go through the long history of the recent ones that you've all heard about that started with very deep supply chain attacks. But they're very difficult to detect. They go unnoticed for a long time. And any of that data that's been collected is now vulnerable to exploitation. So this is another thing that's become, a huge headline maker, is harvest now and decrypt later. Well, it's been going on for thousands of years. Back 2,000 years ago, somebody had to intercept a letter from Caesar to his troops, open it up, hand copy it, and let it go on its way to do that harvesting piece. Well, today that's done everywhere in the world over the internet. No one has to go out physically and connect to a network, tap a piece of copper cable, get in the middle of a radio channel to do that. It's all done over the internet. During the Cold War, that was called the Venona program, run by the CIA and NSA. Hugely successful. All you have to do is break the crypto that they're using or find a flaw in it. The easiest way is, of course, just guessing their keys. If you know that the way they're generating their keys is actually very poorly done and very insecure, then you just guess through all the spectrum of keys, and you could decrypt things in bulk very quickly. The other piece of this is that this was the domain of huge intelligence agencies around the world, less than 5. In the 2000s, we saw China doing this collection on an industrial scale that we've never seen before. The cost of storing this data is almost nothing at this point. You can have huge data farms out in the middle of the Gobi Desert or wherever you want and store that data until you can operationalize it in the future. And again, you don't have to actually do anything to break it. You find the flaws that cybersecurity researchers have already discovered and published on, and then go look for that data and exploit it immediately. It's an incredibly powerful method, and it's only now becoming a really public issue because of quantum computers. With quantum computers, you are absolutely sure that you can break the data. It's not a matter of finding a flaw. It's not a matter of doing research on the people behind it and guessing passwords. You have a quantum computer, you can break the key system that encrypted that data. It's that simple. That change in the priority is a really big deal for the US in particular, because they intend to overtake our economy. And if we don't do something about that now, it's not a national security issue, it's a national economic security issue. They've already taken over huge parts of our economy. We don't know where this goes 10 years from now. They're playing a 100-year game. There was a great movie about this, the Imitation Game, where this is how they did it back in the 1940s to win the Second World War by breaking the Enigma cipher machine. So the question is always, when is Q day? When is Y2Q? That's an analogy to Y2K 2 decades ago. Well, the bad news is that it's already here. So if it takes this long for your data to stay safe, because it's that important, it's government secrets, it's HIPAA compliant records, and it takes you this long to migrate to a quantum safe state, that combined timeline, if that is longer than the amount of time that it takes quantum computers to scale to break it, you have a today problem. It will take a long time. The government already knows this, and they're driving a lot of this change. It's probably going to take at least 10 or 15 years for most large industry. This is famously captured in an equation, which I deleted because no one likes equations, and it's called Moscow's equation. It gives you a very simple indicator of what you should be doing and how you should be reacting and when that time is, and that really is today. It's going to take a long time. Get some folks in your organization familiar with this topic. It's great that you're all here today, and then take some actions. So let's get to the heart of this. It's a little bit of physics here. What makes quantum cryptography quantum? How is it different from regular cryptography? Well, the foundational piece is that ability to just generate a provable random number. And that can only come from modern quantum random number generators. It cannot come from my laptop. Yes, there's some quantum effects in here, but that's not enough to compensate for those predictable behaviors of a computer. So I need to generate a quantum number, and I need that quantum number to be identically replicated in multiple different locations where I intend to encrypt that data. So the most famous way to do that is SneakerNet. If I have to have secure communications between Langley and the Moscow embassy, I have to get a diplomatic courier who literally has a briefcase full of key material that delivers it to that Moscow embassy in a diplomatic pouch every year or every 2 years, whatever it may be. The other way is QKD. QKD is quantum key distribution. I'll describe this a little bit here so you get the general picture of how these systems actually work. That's a quantum secure channel where you have a single unbroken piece of fiber and a physics appliance at that endpoint on each side. This is a sender and a receiver. At the sender side, a quantum random number generator generates a pure random number that tells the sender which states of that quantum state, that qubit that they send over to the receiver. The receiver does the same exact thing on the other side. They pick a random measurement to make on that state. Now those two endpoints have a huge number of random numbers, but they don't match. Now they need a classical channel where they have to authenticate Alice and Bob are who they say they are. Alice sends to Bob and Bob sends to Alice which measurements they made. When their measurements matched, those are when the keys will be identical, and those are the bits that they're going to use from the encryption. Everything else they just throw away. Problem here is that this is not guaranteed by the laws of physics. That quantum channel is, but that classical piece is not, which is why NSA has rejected its use on federal government systems. But there must be a better way to do this, because this, in theory, would be an excellent system to use to get that level of security. But recall that the problems here are fundamental to the way the system is made. I need a dedicated piece of fiber. I need a physics appliance that's outside of my firewalls. It's outside of all my regular data infrastructure. Then when those keys match at those endpoints, I still need to get them to some place where they can use. What's that secure mechanism of getting it to my laptop, my cell phone, and so on? That's why there's, in many respects, the NSA criticism of this and their abandonment of its use. So they're not going to overcome that issue, so this is not a system that we can deploy to solve this problem, but it is part of the solution. So authenticating users, that may be a quantum solution as well in the future, but it's not now. The must-haves that we have from this are that first step, which was making those quantum random numbers so that they've never been replicated. And if you think that's not a huge problem, there was a study done recently where a company went out and harvested 175 million digital certificates. These are the public and private key pairs that authenticate websites or documents and so on. They found that 1 in every 172 shares one of the prime factors, which means it's like having the secret key to that cryptocurrency wallet. I can spoof you, your website, your digital real estate, and there's nothing you can do about it that says that it's not you, because they have your secret key. That's the basis of your entire identity. So the other things that we need is any of these solutions must be globally accessible from almost any endpoint. It can't be dedicated infrastructure that I have to somehow get onto my iPhone or my laptop and be able to use in a hotel like this. So those are kind of critical and foundational issues that we need to get to this next level. So what is the best solution? It's long been known. It's been used for more than half of a century. Again, that's a very expensive, cumbersome system. You have some source in the basement of NSA headquarters that generates a huge amount of key material from quantum entropy sources, which I have a couple slides at the end of this because I know there are questions about that. And then you need to be able to get that key material, again, to those endpoints. And then you need to not use AES encryption, which is just computationally secure. You need something that's information theoretically secure. And the only thing we know right now that's practical is called a one-time pad-based system. And that's really the promise of those QKD systems, is to do that type of encryption. And incidentally, China has already built a network that's thousands of kilometers long to do just that. So they're far ahead of us in building that cybersecurity infrastructure. There's no way to hack that. It's future-proof. So there's a great analogy for this, how this was done during the Cold War. There were random number generator stations, which was a woman on a radio channel just repeating numbers, 7, 3, 5, ad nauseum, all year round, 24 hours a day. These were broadcast into the Soviet Union, Cuba, North Korea, and so on a Monday morning. An asset inside who was never allowed to travel or ever leave the Soviet Union could write down that first sequence of numbers at 9 a.m. His time slot was Thursday at 2 p.m. and maybe another time slot on Saturday at noon. Then he would combine those numbers. That's called an XOR operation. You're destroying information about where they came from and how they were put together. And now you can use that number sequence as a secret key to do one-time pad encryption. Extremely effective, never been broken, but of course nobody's going to do that with their cell phone, so we need a better solution for that. So in the cases where there are facilities overseas, again, that was SneakerNet. You had to hand deliver through diplomatic courier all that key material to that endpoint because you were 100% sure that the Russian government, Soviet government at the time, was collecting all the emanations from that embassy. Every piece of fiber, every piece of communications, radio, whatever it was controlled or monitored by the Russians. So you needed that level of security guarantees because that data has a minimum lifetime of 25 years. In most cases, if it's code word classified, top secret, and so on, it's actually 50 years. And even after 50 years, when it's declassified, almost all of it's blacked out because we need to protect our sources and methods and our assets overseas. That's non-negotiable. We can't count on that computational security of even AES. We have to go to that top level, and that's the best way to do it. Unfortunately, it's very expensive. Until now, it was really impractical. So the point here is that In analogy with how QKD does key generation at the endpoints, we need to eliminate the problem of harvest now and decrypt later by doing the same thing, but using modern infrastructure, not that 1970s PKI architecture, which incidentally is not fully deployed globally. Some estimates say we're only about 60% of the way there, and a lot of that's for websites. We also need to have another piece of change in this architecture. We need to decouple the mechanism that makes the keys at the endpoint from the software and the mechanism that encrypts the data and distributes it around the world. We've packaged that now because it's really easy to exchange cat videos with an HTTPS connection, but the future is an HTTPQ connection where we don't have that happening anymore. We're generating keys that are unknowable to the cloud or the mechanism that made them, and they're decoupled from the people who distribute that data. So when I'm sending a chat message, and we'll do an example, that I had a request to do an example of that today, and so that the people that are running that network, that messaging service, whatever it may be, have no chance of accessing the key material because they were not part of the process of making it. They're just a transport mechanism and all the bells and whistles and emojis that you want to use, but they can't actually see any of the data. So a quantum solution looks very different from a classical solution. On the bottom left side, it's the classical case of Alice and Bob. They start an asymmetric key exchange. The public and private keys are now used to exchange a symmetric key. That symmetric key uses that channel to encrypt the data back and forth between Bob and Alice for as long as that channel remains static. And then on the right, we have a more modern version where now we have these quantum entropy services in the cloud. They're a constellation of physics appliances that are in multiple different data centers, geographically separated in different legal jurisdictions. So there's no one point of failure or attack or compromise by any big government. So if you had one in China, you want some in Europe, and you want some in South America, so there's no single government that could ever get control over that channel. And that channel, this is a very high-level picture, will do two things. Alice and Bob will now establish that same asymmetric channel between them, that PQC secure channel. Even classically, you can use RSA in this case. And instead of exchanging that symmetric key that you see on the left, all we're going to do is exchange a small amount of encrypted metadata. That's well within the parameters of operations for small data sets that asymmetric algorithms are useful for. That metadata will contain a couple pieces of information. The first piece is which of those entropy sources in the cloud do I, Alice, have access to? Bob will say the same exact thing. Well, I have access to 17, 94, and 148 cloud servers. And then Alice and Bob will now agree that those are the servers we're going to use to establish our connection. And each on one of those servers, they operate in two modes. The first mode is like that radio station I described. They just broadcast random numbers all the time. The second is in a static mode where you have a huge repository of that quantum random on the cloud that's overwritten on an hourly basis. Now Alice and Bob will go to each one of those cloud repositories, simple API calls. They'll download specific strings of random numbers at each one of those cloud repositories, download it to their endpoint, and they'll concatenate them to one giant pool of random that they now both have at each of their endpoints. So Alice and Bob have now succeeded in generating huge amounts of quantum random, just like QKD, at their endpoints, but they don't match. They don't match because I can't use that for key material because the cloud theoretically was an adversary. They stored all the information that I download, so that's not useful for generating keys because I have to trust the cloud provider too much. So the last piece of metadata is something called cryptographic extractors. I won't put any equations on the board, but they take a large amount of random and they distill it down by destroying a lot of that information in something that's a single key. And the recipe for how to do that is unique to every one of these sessions. So it's not like if I knew the random numbers that were used, I still need to know the parameters for these extractors to generate that unique key for that session, that I have those quantum assurances that it's never been replicated. It's never been used ever before. That case that I gave with the certificates before should never have happened twice in the history of the universe, and it's happened hundreds and hundreds of thousands of times. That's demonstrable and testable by anybody on the internet. That should never happen twice. So this process is called sample and extract. If you imagine the top layer there is a bunch of the different cloud entropy as a service servers. The red boxes are the ones that Alice and Bob can both see. and from which they extract these small strings, these small bits of random from each one of those servers. They bring them down to their endpoints, and now they have a matching set of random numbers that are generated from quantum entropy sources, and then the pipe at the bottom is really how to distill that and extract a single symmetric key. And that can be an AES key, computationally secure, or a full one-time pad-based system like the QKD systems that can be used for absolute information theoretic security. At that point, if that's the encryption method that you're using, let everyone in the world harvest that data, post it on your Facebook page. Who cares if they harvest it? They can't do anything with it. It's provably secure against everything, not just quantum computers. So the point here is that for each part of this system, you still have to be crypto agile. There's a compliance issue in most industries to use these new PQC algorithms that NIST is advocating for. But you don't have to use them in the way that they're normally used, which is to exchange symmetric keys. You can use them in a system like this where you have a much higher level of assurance. So practical application where you can see something like this being used, I'm going to get the cane pull soon, is a messaging application that everyone uses every day. At the bottom is the quantum entropy service. You have lots of those servers in the cloud from different locations. Alice and Bob each reach out to those servers. This is independent of the messaging network to download the key material. They generate their keys at the endpoints, and now they can use the Mattermost, which is an open source messaging platform that lots of folks use for free, and use that network that they've already built to make all those things happen, the encryption of the message, the transport of the message, the linking up of address books between users and so on. But the Mattermost server can never do anything with that data. They were never part of the process that encrypted that data or generated the key material. I'm going to go a little faster. There's no free lunches in cryptography. You have to pay somewhere. Bigger, stronger, more powerful algorithms require more compute resources on your endpoint. They require a lot more complexity. They require more processing power and more advanced systems. You need all of these things to be compliant with the standards that are coming out, and you need to be crypto agile. Be prepared to swap them out at any time. And you should not have to trust anyone. If something is truly end-to-end encrypted, if your vendor, software, hardware, is really telling you that we can't see anything or do anything with you, you should test that. You should have those guarantees in writing. Because if they're the software provider that's also part of that key generation mechanism, although they may be end-to-end encrypted secure, it's not from them. They can see what you're inputting client side. So if an adversary is on your endpoint, whether that's a friendly or an attacker, they see what you see. No amount of encryption helps you. So that end-to-end security guarantee is just false. It's not secure from them. It's only secure in transport. You don't want anything like a backdoor in existence. And the US government, I worked for the government for 2 decades. I've never heard of anyone advocating for a backdoor except for law enforcement. It makes their job much harder for catching pedophiles and terrorists and so on. I get that. But the cost to the US has been so high from suffering from these older systems and the exploitation of them by our adversaries for the few extra people that we're going to put in jail. It's just not worth it. I don't want my kids working for Huawei one day, so this is really a national economic security imperative. We really have to do something about this collectively, and we have to move faster. We're not going fast enough today. So I think the key escrow idea and the backdoors advocated by the government have gone the way of the dodo. They appear periodically, but I don't anticipate them going anywhere. In this process, we're in the late phases of this right now. As I mentioned earlier, that key exchange mechanism, that asymmetric piece, there's only one algorithm left for standardization next year, and that's known as Kyber. Again, we don't know if this will break. There's no proof that it's an actual hard problem. We know that it's definitely better than RSA and elliptical curves. We have to transition. Those are for sure broken by quantum computers. They would never have been standardized if quantum computers were invented first, or known about at least. That's the situation we're in today. We have to transition. This will happen. Lots of systems, legacy systems will break. They will be completely dysfunctional, need to be replaced. So you think about now what you're buying for the next 5 or 10 years, they have to be compatible with these algorithms. If you're selling to the US government, they just won't buy them. They won't be able to integrate with you. On the signature side, it's a little beyond the scope today, but we're concerned about all the signatures that are out there today. NIST is asking for new fourth-round candidates for possible standardization a few years from now. We just don't know. So the situation we started with, 80-plus algorithms, almost all of them have fallen one way or another or been deprecated for one reason or another. We're down to almost a single point of failure with Kyber, which is every TLS connection, every enterprise data exchange you're doing on your network, any place you see an arrow on your architecture. Government's really driving this. There's been multiple national security memorandums telling us that we have to transition, we have to address this issue of harvest now and decrypt later. China will overtake us if we don't do something about it today. There's been legislation, bipartisan support, and multiple executive orders that are really driving this all within the last 18 months. We have to do this, and the government is pushing it. Remember, the government's a Fortune 0 company. They make more revenue than all the other top 9, 10, whatever have you combined. It's trillions of dollars. And they have told you, if you're a vendor to the US government, you're in hardware, you're in software, services, whatever, if you are not PQC compliant, we're not buying from you. We can't do business with you. We can't even connect to your network infrastructure as a contractor. You have to do this. 10 minutes, okay. So the process is going to be long. We have never finished the first one that started 20 years ago when the internet was minuscule. It was tiny. The data structures and complexity that we had back then are nothing like what we see today. The cloud, all these different technologies that we enjoy and love every day just didn't exist. And now we're doing something that's never happened in IT and security history. We're in completely uncharted territory. We don't know what kind of things will break. We're seeing smart cities being connected. We're seeing vehicles that will be on the road for 10 or 20 years. People are talking about buying Teslas that are good for 500,000 miles. Those will be on the road 20 years from now. If the security of those systems is compromised, they can be drawn into telephone poles. They can do all kinds of damage that we can't even predict today. IoT devices and things like smart sensors, smart grid, critical infrastructure were never meant to be connected. They were secured by physical pieces of wire and fiber and Ethernet. We're now connecting this to the internet. Stuxnet happened over a decade ago. People still have not addressed those problems. That was science fiction level technology that came out back then. It's a decade old. There's no cybersecurity professional that has ever published anything about that attack even being possible. Can you imagine the kind of tools that intelligence agencies around the world are developing today that are unimaginable? They're coming out now, and it's going to affect this type of infrastructure. So we have to get harder, stronger, and faster. I'm going to end there. I have a couple more slides on some other questions that you all asked, but I'd rather answer your questions rather than go on to what is entropy and what does that really mean for us. So, anyone? Yeah. Do we have a mic? I'll repeat your. That's good. I'll repeat your question.
So, how do you is that commercially scalable to do the in the cloud random generation filtering piece on this? Like, if you look at an e-commerce site and how many transactions they process every second, is that feasible?
Absolutely. So before these sources could only operate at bits per second, per minute, and so on. They've now reached multi-gigabit per second speeds, so it's not an issue. Here you pay by having to download that quantum random for the cloud. There's always a price in cryptography. You pay one way or another. You pay with poorer security, or you pay in some bit of complexity or other costs. So that's commercially available, and that's really the financial industry is driving this. I mentioned before one of the bodies that does this. They're very concerned about this because they have vast investment in IT, and a lot of those IT systems are now connecting to their OT systems and their data centers and the critical infrastructure that they run for their own business. So they're ahead of the game. They have money to do it. The government, of course, and similar industries that we deal with.
So then can I dovetail into, so we have browser compatibility issues with people with old computers now. I don't see how you can solve that because you can't get grandma to do other things.
Yeah.
I changed my dad's iOS the other day and freaked out.
Yeah, well, it's the old adage, how fast do you have to be to outrun a bear? Just faster than the guy next to you. So if you're secure, you can't help that guy, Everyone's not going to do this. It's not possible. We've never done this before in history. This isn't like, TLS 5.0. This has not ever been done before. So uncharted territory, I just recommend for my children's future's sake that they have jobs here in America one day, that every large enterprise start now and doing something to implement some of these systems. At least go out and do a proof of concept, get familiar with it, see what breaks, see how it works, get smart on quantum, assign one person to come to conferences like this and learn about it. Question? Oh, yeah.
In the portion of the algorithm that you described,
I'm hard of hearing, sorry.
In the portion of the algorithm that you described, where both parties were looking at the state of quantum entropy to derive keys, is there a time dependency where they both had to be observing it at the same time, or is the observation separate from concurrent? Like,
That's a great question. So if you're online at the same time, I'm sorry. Yeah, so the question is, for that algorithm operating in the two modes, synchronous and asynchronous. Synchronous is you're both online at the same time, you're communicating at the same time, so that's the easy case. What if you're asynchronous? What if I send you a message and you don't open that message for 2 weeks? Well, that's a parameter that the enterprise that runs that network would set. They want a time to live for that quantum random in the cloud to be 2 weeks. Otherwise, you have to resend the message. No, it's overwritten. It's stored in the cloud. It's accessible. We do it right now for an hour. So you have an hour to synchronize and download and decrypt that message, or it has to be resent with a new key. And you want that. You don't want that stuff to be persistent either. You don't want the key material, nor the things that generated any of those ephemeral keys to be available anywhere again. You want them to die.
I was just under the impression that the simultaneous observation of the quantum state would be what you would derive the key from, but that doesn't seem.
The key is derived in the last step at the endpoint. You only downloaded the raw materials and the SDKs to do this operation from the cloud. The last piece only happens at the endpoint. Those are the extraction parameters that you apply to that random that effectively distill it down into a symmetric key.
Thank you.
Can you speak a little bit on the cost differences between using a quantum type system versus a traditional symmetric or asymmetric key?
Yeah. So those are free, the last ones, because they're generated from regular noise on your computer. Quantum, the price of this used to be very high, of course. You needed an entire rack. Some of those sources were radioactive inside. You couldn't put that in a data center. They were in the basement of NSA headquarters. But now they're actually done completely photonically. So they fit in a server rack that goes into a data center, and they're really cheap. That's not the big cost in this. It's marginal for messaging, and unless you're doing huge amounts of data transfers, huge amounts of data files, you wouldn't notice any difference.
How does the sender and receiver agree on those extraction parameters you were talking about?
Those are the PQC exchange, so it's the same asymmetric key exchange that you did for doing symmetric keys, but you're now exchanging a small amount of metadata. That metadata tells you which servers we both had access to in which geographic regions, and which strings in those repositories on those servers. Some of those might be dedicated to your company alone. Only my company employees can authenticate to these strings. But the last set, the piece of the parameters that the cloud will never know, is what happened between Alice and Bob, is how do I apply those extractors to get a unique key at my endpoints that no one else knows about. That's true end-to-end encryption. That's true key derivation at the endpoint and not delivery in between.
Follow up on the same types of questions about the quantum metadata. If Alice and Bob, in your architecture you had about like the quantum solution, if they're still receiving that same quantum metadata, how are we avoiding like the same sort of like harvest and decrypt risk, assuming an adversary is already tapping the network traffic? I know you noticed at the endpoint,
Yeah, yeah.
you're screwed anyway, but what about?
So let's maybe go back to the diagram. Yeah, so here, the PQC exchange, it's ephemeral. That data that you exchange is only useful for the time that those servers are available, whether they're in streaming mode or before they're completely overwritten. So if an adversary captures that PQC exchange, and they, in the future, decrypt it with a quantum computer, let's say we believe that they will be authenticated users to the same service. They will have access to the same cloud service. But when they go back to download those same strings, they've changed. They don't have a time machine to go backwards in time to recover those.
So if Ivan's in the middle there,
Ivan?
then, and Teeth, yes, I'm sorry, that's,
No, we're going to Russian.
I learned my cryptography probably a few years before it was inappropriate to say, yeah. So you've got an attacker in the middle there, kind of eavesdropping during this PQC. What's to prevent them just from grabbing the strings at that point in time and then encrypting the message?
Because it goes, I think it's at the top of the string. If an attacker sees everything you see at your endpoint since inception of that device, then no crypto helps you anyway. Yeah, you're screwed. They've got you. They're on your endpoint. So if they see everything coming in and out of that endpoint since its inception, and I skipped over other pieces in this that make that even stronger, but if they have, the example is you bought an iPhone in North Korea. The North Korean government has seen every single packet that's coming in and out of that device. Yeah, then you only have computational security. You do not have information theoretic security. But if they've ever missed anything, any one API call, any connection, any part of that PQC metadata exchange, it's an all or nothing proposition. You get nothing.
Have there been any experiments with taking advantage of entanglement for
Yes.
random data?
Yes, and one of the largest ones actually was revealed today. It was in China. They built a single QKD link that was 1,000 kilometers long. So they can now connect with a single unbroken piece of fiber, a 1,000 kilometer long node. And I'll put this question out to you today. An AES key is 256 bits. In this system, you can generate, 100,000 AES keys per second. In that QKD example that China just did, first ever in a monumental achievement in physics, how long do you think it would take to transmit a single AES key on that network? Throw a number out there, something crazy. 20 hours. It can't do a bit per second. You're talking about fractions of a bit every hour. So the QKD, I got the STFU sign. Sorry.